What if the reason some people respond perfectly to a medication and others do not has less to do with the prescription and more to do with what is living in their gut? In 2026, a massive diet-to-microbe map made that idea measurable. The human gut microbiome functions as an active biochemical filter. Prior to 2026, the medical consensus viewed this ecosystem primarily as a supportive digestive network. Textbooks defined its role as breaking down complex fibers, synthesizing vitamins like B12, producing short-chain fatty acids like butyrate, training the immune system, and maintaining intestinal barrier integrity. However, this framework expanded drastically with the rise of pharmacomicrobiomics. Clinical studies published in journals like Nature demonstrated that microbes act as direct pharmacological gatekeepers. They utilize specific enzymes to activate, inactivate, reactivate, or physically sequester over 150 common medications. For example, gut bacteria secrete beta-glucuronidase, an enzyme that reactivates the chemotherapy drug irinotecan in the intestine, driving severe gastrointestinal toxicity in up to 40% of patients. This step-by-step enzymatic interference explains the massive variability in pharmacokinetics and pharmacodynamics across different individuals. The definitive catalyst for controlling this variability was the 2026 Human Phenotype Project. Researchers published a high-resolution diet-to-microbe dictionary based on comprehensive data from 100,000 individuals. This database accurately maps exact dietary inputs to specific bacterial enzyme outputs. Physicians can now predict and tune these precise drug-relevant microbial functions simply by prescribing targeted dietary modifications before administering pharmaceuticals. To understand how we can tune these functions, we first need to look at exactly what pharmacomicrobiomics is measuring. Pharmacomicrobiomics is the precise study of how microbiome variations alter drug pharmacokinetics, meaning absorption, distribution, metabolism, and excretion, as well as pharmacodynamics, which dictates efficacy and toxicity. Your microbes interact with oral medications at two critical stages. First, they encounter the drug before it is even absorbed into your bloodstream. Second, they interact with it again during enterohepatic recirculation. This is a process where the host liver processes the drug, secretes it into bile, and sends it back into the colon, where microbes can deconjugate or modify it again. The reason this matters is that your microbiome possesses roughly 3.3 million genes, representing an enzymatic repertoire 150 times larger than the human genome. This vast microbial engine specializes in reductive, hydrolytic, and fermentative chemistry that your liver simply cannot replicate. Because of this unique metabolic capacity, the microbiome operates as an invisible, supplementary second liver that actively controls the bioavailability of the medications you swallow. With this second liver concept in place, we can break down the exact mechanisms these bacteria use to control drug outcomes. The microbiome controls drug effectiveness through four highly specific direct mechanisms. First is activation. Bacteria can convert inert prodrugs into active forms. We see this when bacterial azoreductases from species like Lactobacillus cleave the azo bond in sulfasalazine, releasing the active anti-inflammatory medication locally in the colon. Second is inactivation. Microbial pathways can destroy or modify active drugs, lowering their effectiveness in the body. A concrete example is how specific strains of Eggethella lenta carry an operon that inactivates the cardiac failure drug digoxin in about 10% of patients. Third is reactivation. Your liver will often detoxify chemotherapy drugs like irinotecan, but bacterial enzymes in the colon can strip away those protective modifications, reactivating toxic metabolites and causing severe side effects. Finally, there is sequestration. Bacteria can physically bind or trap drugs inside their own cells or biofilms, completely preventing absorption into your bloodstream. Knowing these mechanisms exist is entirely different from being able to predict them, which is exactly what the 2026 data solved. The 2026 Human Phenotype Project mapped the gut microbiomes of 10,068 participants, generating the largest and most robust diet-to-microbe associations ever recorded. Published across major scientific journals, including Nature Medicine, this study demonstrated that diet reliably predicts both the presence of specific microbial species and their corresponding functional pathways. The key finding was the astonishing strength and longitudinal persistence of these predictions over time, because the data links specific foods directly to the bacterial enzymes responsible for drug metabolism. The clinical implications are immediate and immense. Medical professionals can now use pre-prescription microbiome and diet profiling to anticipate exactly how a patient will process a medication. By prescribing targeted dietary adjustments alongside a drug, clinicians can actively tune the microbial ecosystem to ensure a medication is activated, prevent it from being degraded, and drastically reduce the risk of toxic side effects. This massive dataset transforms our relationship with medication from a game of chance into a predictable, engineered outcome. The main takeaway is a profound paradigm shift in modern medicine. The gut microbiome is a tunable pharmacological gatekeeper, not just a passive digestive companion. The 2026 Human Phenotype Project made diet-to-microbe prediction actionable at scale, enabling practical clinical pathways for microbiome-aware prescribing and targeted diet adjustments to improve drug efficacy and reduce side effects. As the field advances toward causal drug-specific trials, the way you eat will become just as prescribed as the medications you take. Thank you for watching, and I will see you in the next breakdown.